All right, so we've now seen how a seismometer works. The question is, how do you read the record that comes out of a seismometer? Well, the record typically is called a seismogram, and seismologists have learned how to interpret pretty much every little bump and jag that you see on a seismogram. So let's look at a simple example. The first jog that we see, the first wave of the earthquake that arrives, is the P wave. The P wave is a compressional wave that passes through the body of the Earth. Vibrations happen after the P wave for a while until another jag comes along or another bump comes along, and that bump is the S wave, or the secondary wave. It arrives later because it does not travel as fast as it passes through the body of the Earth. Secondary wave is a shear wave. Then a little more time passes, a few more vibrations pass by, and then suddenly the size of the vibrations recorded by the seismograph increase dramatically. This represents the arrival of the surface waves, the Love waves and the Rayleigh waves. Typically, the surface waves have larger amplitudes at a given location than the P wave or the S waves, and they tend to last a longer period of time. Why do these earthquake waves arrive at different times? It's simply because they travel at different speeds. The faster waves arrive earlier, and the slower waves arrive later. Okay, how do we translate this information into a measure of the size of an earthquake? Well, the key to this challenge is to somehow normalize measurements so that the measurement that you record at an instrument or a seismometer that's very far from the earthquake epicenter can be translated into the same numbers as the record of an earthquake that you record at a seismometer that's close by. One of the first people to think through this problem and come up with a solution was Charles Richter. And the way he came up with solving this problem resulted in what's now known as the Richter scale. And it was one of the earliest scales used to measure the size of an earthquake objectively. Basically, Richter's solution is very simple. What he did was he measured the amplitude of the largest earthquake wave recorded at a seismometer and normalized so that he translated that into the amplitude that the earthquake would have at a distance of 100 kilometers from the epicenter. So when you read about an earthquake in the news media today, the number that you see is often referred to as the Richter magnitude. But in fact, it's not, because the Richter magnitude uses a very special scale that's really often relevant only for nearby earthquakes. The number that they're actually using, and the number of record for an earthquake, is called the moment magnitude. And a moment magnitude is determined using a somewhat complicated calculation that involves measuring the area of the fault that slips, the amount of slip that takes place on the fault, and also the strength of the rock in the vicinity of the fault. In fact, usually what happens is you'll get an earthquake magnitude that's reported almost immediately, and that's something more analogous to a Richter magnitude. And then sometime later, you'll see a correction to that, and that correction that appears later is the moment magnitude, because it takes time to do that calculation. One of the things that's important to recognize at this point, and I want to emphasize, is that the magnitude of an earthquake, something like the Richter magnitude or the moment magnitude, is a different number than the intensity of the earthquake, or what we called earlier the Mercalli intensity of the earthquake. Again, that's because the intensity is based on a measure of damage, and it's going to vary with distance from the epicenter, whereas the magnitude of an earthquake is a number that's based on a measurement off of a seismogram and can be normalized so that you'll get the same number of magnitude regardless of where you are around the world for a given earthquake.